Good afternoon, children. Now today we are going to talk about magnetic force on a current carrying conductor. I will repeat the concept which we talked about yesterday. We talked about that when a given charge moves in a magnetic field B, see if magnetic field is like this, and the charge Q say starts or enters into the magnetic field with velocity v, making an angle theta with magnetic field, the magnetic force or the magnetic Lorentz force experienced by it is given by F is equals to Q V B sine theta. And in vector notation, it can be written as Q V cross B. From this expression, we can also find out when can be F maximum or the magnetic force maximum. You can write down Fm also for convenience. When is the magnetic force maximum or when it is minimum? You can see from this expression, Fm will be maximum when sine theta is equals to 1 or theta is equals to 90 degree. That is, maximum force will be experienced by the charged particle Q if it enters the magnetic field in a direction perpendicular to it, and it will keep on decreasing. See, when will be F minimum? When sine theta is equals to 0, this is one condition, or theta is equals to 0, or else V is 0. So these are the two conditions for minimum force. So you can see that as it will keep on making or entering into the magnetic field with making an angle theta, as theta keeps on decreasing, the force will start becoming minimum. And if the charged particle enters parallel to the magnetic field, minimum force will be experienced by it. And other condition in which force is minimum is V is 0, means if you put the charged particle inside a magnetic field but it is not moving, the velocity is 0, then also no force will be experienced by it. From this we are now able to find out the magnitude. Second thing is direction. Now from the vector product, as F is a vector product of V and B, therefore the direction of F will be perpendicular to both V as well as B. We'll also see it pictorial. Now we'll talk about magnetic force on a current carrying conductor. Now what is the difference between this expression and this expression? Here we are talking about a single charge. A charge Q is moving. When we talk about current carrying conductor, many charges are going to move. So first we'll have to find out how many charges are moving in a conductor. So what we'll do now, we'll consider a conductor of say given length, say L, area of cross section A, let there be charges or electrons moving with say drift velocity Vd. This conductor is say placed in a magnetic field. For convenience, perpendicular, maximum force will be experienced. Later on we are going to introduce theta also. So this is the situation. One more thing which we have to assume is, let n is number of charges per unit volume. Now we are going to talk about magnetic force, so the formula will be this. We'll use this formula. Fm is equals to Q V cross B, and since here the velocity we have taken as drift velocity, I'll change it to this. This can be taken as equation number 1. So the main aim is to find out now how many charges. So Q is equals to what? Total number of charges multiplied by charge on one electron. So how many charges will be there? See, N is the number of charges per unit volume. Then the total number of charges, if I take it as say capital 1, capital N, total charges N multiplied by E. How many total number of charges are there now? First I'll find out the volume, this because N is per unit volume. What will be the volume of this conductor? A L. How many number of electrons or charges? Multiplied by N. So N A L E. This will be the total amount of charge. Air is a volume, number of electrons or charges per unit volume. So total number of charges NaL, total amount of charge will be multiplied by charge on one electron. So this is not all. So Q shall be replaced by this number. So Fm is equals to NaLe Vd cross B. Now this can be replaced by another term. As we already know from our second unit, I is equals to NeAVD. Now Vd is a vector quantity because here we are using it in vector notation, but I is a scalar quantity. How to convert so that we can introduce vector on both the sides? Because if this is a vector quantity, we shall have a vector this side also, because here we don't have any other vector. Now to convert current into a vector quantity, because we know that current has direction but cannot be treated as a vector quantity. So to make it a vector, what we do is we multiply it by the length, and this length will be now treated as a vector quantity, and this will be known as a current element also. NeALV. So what we have done is we have multiplied both sides by L, and now on both the sides we'll have a vector notation. See, vector is being noted here above L, but it is the direction of current. So how will you treat it? It is the length in which current is moving, but the direction of current is being introduced on L. Now substitute NeALVD. This will be replaced. So Fm is equals to IL cross B. We can write it there. This much can be written as IL cross B. So Fm is equals to ILB sine theta. And simply, if theta is 90 degree at maximum force, so Fm will be equal to BIL. So force will be experienced by the length L. The current, instead of charge we have introduced now current here, and this is the magnetic field. So the force experienced will be BIL. This is the maximum force. If it is making an angle theta, it will be BIL sine theta. Now from the same expression, we can also find out the unit of magnetic field. You can try doing it on your own. We have already talked about how you are able to find out the unit of a given quantity from its formula. So you can find out from here. B is equals to F upon Q V sine theta. You know the unit of F, you know the unit of Q, you know the unit of V. So from here you can find out the unit of magnetic field. Now to denote the direction on the paper, what we do is, magnetic field is represented in two manners. One is cross, like this. If I want to represent a magnetic field on the plane of the paper, I can put crosses like this. And what does it indicate? It is magnetic field into the plane of the paper. Because most of the time, see, we are dealing with three quantities: force, velocity, and magnetic field. Father, mother, and child. Velocity, direction of velocity will give me the direction of current also. It will be in the opposite direction of the motion of the electrons. And if positive charges are moving, it will be in the direction of positive charges. So now since three things we'll be dealing with most of the time. So what we have done is, we can represent magnetic field in the plane of the paper so that the other two can be made in the plane of the paper. So B, when represented like this, means it is perpendicular to the plane of the blackboard or paper if you are using, but it is inside, going like this to the plane. And if we denote it like with dots like this, since dots are not very clear on a paper, so we can do one thing, we can put dots with the circle lines. This also you can do. And it will indicate a magnetic field perpendicular to the plane of the paper, but the direction is coming outside. Like how can we do it? Suppose a charged particle, say Q, enters the magnetic field. Now, so according to the left hand rule, father, mother, child, you can do it like this. See now, magnetic field is into the plane of the paper. The charge is moving towards right side. The force will be in upward direction. So the force will be like this. And if the force is like this, the charged particle will be attracted towards this side. So it is going to follow a circular path. Now you can see at each and every point. See, if the velocity is in this direction, force will be in this direction. Velocity in this direction, force in this direction. Velocity in this direction, force in this direction. So if a charged particle is entering a magnetic field in a perpendicular direction, it is going to follow exactly a circular path. And since no other force is there, only magnetic force is there, and for a circular path, centripetal force is required. So all the centripetal force which is required by this charged particle to move in a circular manner is provided by this magnetic force. That is mv square upon r is equals to bqv sine theta. If we are taking, see here, since theta will be 90 degrees, so this we can neglect. So this is the expression which is going to be followed. This concept is very, very important, is being used in, we'll be talking about a device, cyclotron, particle accelerator. This is the main concept which we'll be using in the working of that device. So this formula you have to learn, understand, and how to apply is very important. So we'll go through this topic today. Till here, then we'll talk about if the particle is making an angle theta already, then will the path will change or it will remain in the same manner? That we'll try to do tomorrow, and we'll talk about a device cyclotron.